So I'm not sure whether I can finish in time today. So this is the Pairwise sequence alignment. So most of the things have been taken from the book Bioinformatics and the Functional Genomics. I'll try to share the chapter with you. Very good. Okay. So we'll be looking at the homology and the orthologs and the paralogs. We already know about these terms. Can you hear me properly or?
Yeah, Maksud, I can hear you properly. Is it okay, Akbar? Are you listening it properly?
Yes, sir. The audio is fine.
Okay, thanks.
So then we're looking the pairwise alignment. So pairwise means I use compare the two pair that means the two sequences, and we're looking at some of the algorithms. But I'm not going to the I'll just look into the one or two algorithms, but not all of them. And I don't think that we can go through the PAM matrices and the boson matrices today, but I'll try to explain them in the next class. So this. So pairwise sequence alignment, this is a most fundamental operation in bioinformatics. So what do you do in the pairwise alignment? We compare the two sequences, and basically want to see there is an assumption such that if the two sequences are similar, actually, so they have their structurally and the functionally similar. So say, for example, if you're given a sequence and you want to find the structure or the function of the protein or the nucleotide sequences, what do you know to do? So you can compare that with the sequence which has a known structure and the function. So if they're similar to each other, so the unknown, for example, this is your sequence and this is the known sequence. So this is your sequence, that's unknown, and this is a known sequence. Yeah. So and its structure and function is known, but yours one is unknown. So what you can do, you can compare that, and if they're similar, so there are certain metrics. So looking at that. So if they're similar, they have a similar sequences. So this is your unknown, this is your known, and if they have a similar sequences, they might have similar function and similar structure. That's one of the reasons we do the pairwise alignment. And sometimes what happens, you have two sequences and it has the protein motifs and the domains. So you can compare them. For example, this is your sequence and this sequence, another sequence which motifs are known. And you can find that there's certain conserved region between them. And this is, for example, this motif or domain might be absent. So through the pairwise comparison, sequence comparison, you can find the location of the motifs and the domains and the conservation of the motifs or the gain or loss of motifs. And Wakas will describe in details in the next lecture 7 on the BLAST. And it is also used for the analysis of the genes and the genomes. So sequence alignment. So which one is better to use, DNA or the protein? So protein sequences are more informative than the DNA because you can see that there are 20 amino acids usually, and in DNA you have only 4 characters. So and many amino acids also share the similar biophysical properties. Say for example, so in the third codon, okay, so for example, like you may have certain sequences A, T, G, or A, T something else here. So, but both of them, say for example, codes for the methionine. So if you if you align the DNA sequences, you can find that there is a polymorphism. There is a change in the nucleotide. But in actual world, actually, because both of them codes for the same amino acid, so E is better. So aligning the amino acid protein sequences is amino acid sequences are more informative than aligning the DNA nucleotide sequences, because especially in the third codon. So there might be changes in the nucleotide, but there might not be change in the amino acid, and sometimes might be changed the valine, but both of them have the same properties. So these are the things you need to take. Sometimes we need to take into considerations. And as you said, the codons are degenerated. So changes in the third position often do not alter the amino acid that is specified. So in that case, it's better to use the amino acid alignment. And also for the also the protein sequence can be used as a chronometers. I'm not going to the details. So for example, sometimes you don't get matches using the DNA sequences, but certain, yeah, but for the searching for the plant globules using human beta globule protein yields many matches. So these are certain things. Sorry. So that's the problem with the MacBook. I have to click on the pen again and again repeatedly. So many times actually. So the DNA alignments are very useful. For example, the you're aligning the sequences here, and you want to look into like the upstream regions or the regulatory regions or the non-coding, the intronic parts. Yeah. So you want to see if it changes the introns or the non-coding regions. So in that case, it's actually in that case it's useful to align the DNA sequence to align the DNA sequences. Sometimes you want to look into the polymorphism like SNPs or the single nucleotide polymorphisms. In those cases, we look in the details of when you do the human genome analysis, and also the genome sequencing relies on the DNA analysis. So what is pairwise alignment? Pairwise alignment is actually the process of aligning of the two sequences and to achieve the maximum level of identity. And also find the degree of similarity and the possibility of homologous. So what is, we look at the terminology very soon, so explain it. So similarity attributed a descent from a common ancestor. For example, if the two sequences, for example, came from the same ancestor, they're called homolog. Yeah. And identity is, for example, like X, Y, sorry, A, B, C, D, or something like that. Yeah. So for example, this is C prime. So how many of them are identical? There are two identical. So that means 2 divided by 4 is 100. 50% identical. But C and C prime, these are not identical, but they're similar amino acid. So the similarity is 75%. So this is the difference between the identity and the similarities. Identity means the amino acid which are identical to each other, and sometimes amino acid gets changed, but change with the similar amino acid, the similar properties. So in that we call them the similar. So I'll look, we'll look into one of the alignments, and that will be easier to understand. So identity is the two sequences, the percentage of identical sequences, and similarity is actually it includes the identical sequences as well as the similar sequences. And also the conservation, as we said, for example, as we said, the A, B, C and the A, B, C prime. So that's change, that's a conservation actually, although that change has been made, but this is conserved because the change is made with a similar amino acid. Okay, and these terms we need to understand very carefully. So the difference between the homology and the similarity. So homology is basically the sequences that came from the same ancestor. They might or may usually they're similar, but they're not similar. But similarity actually is a like quantitative attribute. We can say how much similar two sequences are. Yeah. Say for example, between these two sequences, the length of the sequences, for example, 50 base pair. The similarity is, for example, 5 nucleotides, 5 base pairs similar. So we can say that 5 by 10, the 50% similarity. Yeah, but we can never say that the 50% homologous. Usually homologous sequences are, or we can say the similar, but not, but we cannot say that we can. This is a qualitative. And as we said, they should come from the same ancestor. So this is global homologs in human. And from the, for example, myoglobin, my hemoglobin, tetramer, and the beta globin and the pair. So this is a pairwise alignment, the beta globin and the hemoglobin. So you can compare this structural comparison between these two protein molecules. Okay, now comes the orthologs. So homologous sequences in different species. Say for example, this is a gene, yeah, that came from the same ancestor, and he found this gene, the same gene in the two different organisms. And we call them the ortholog. Yeah. And homologous sequences within single species. For example, so this is the same species, and this is due to the gene duplication. For example, you can see here the orthologs, the myoglobin found in the different organisms, humans, chimpanzee, orangutan. So this myoglobin, actually we call them the orthologs in different organisms. And in the same way, the paralog, the member of a gene family within a species. For example, the globin found within the human. So this the same gene. You see the difference in the previous slide. What we found is actually, so that's the same gene found in the different organisms. But here, what we found is the homologous genes found in the same organisms. This could be due to gene duplication, and that's a process of evolution. That's a evolutionary, one of the evolutionary process. So for often been in a single tree, for example, this is homologs, and you can see here the orthologs, the frog alpha globin, chicken alpha globin, mouse alpha globin, we call them orthologs. And for example, this mouse alpha globin and the mouse beta globin, they're also homolog, but they're both found in the same organism, the mouse. So they're parallel to each other. So how do you align the sequences? There are different methods by hand. So that's not very useful, and that's not very wise to do if you have a longer sequences. Then one of the old methods is a dot plot. So we looked at that, and there are rigorous mathematical approaches. There are dynamic programming, but they're slow, but they're very optimal, and they give it almost accurate results, and blast and faster word matching the hash table. So that is explained by Wakas in the next class. So align by hand. How do you do that actually? Say for example, that will be yeah. So there are two sequences. For example, you can align them something like that. So you can put the gaps here, or you can align something like that. A, T, G, C, C. Yeah. So that's by hand. You can do that. Yeah. But if you have the larger sequences, but it's not good to do. So you can do. You need to do the computer and. So person sequence similarity. So how many sequences are identical to each other? For example, the length of the total size of the alignment is the 10 total length, and identical sequence, and the math identical sequences are 7. So we can say that 70% identical, and these are, we call the indels, or the insertion of the deletion. So we need to put the insertion of the deletion. So this is the insertion, we call them. So yeah, sorry, this is the insertion, and this is the deletion for this sequence, and insertion for these sequences. So sometimes you need to put the gaps to properly align the sequences to find the best matching regions within the sequences. So you need to choose two sequences, and you need to select an algorithm that generates a score, and you can, as you said, that you can provide the insertion and the deletions, and degree of similarity defined. It can be global or the local. So global alignment is, for example, if you want to have the two sequences, yeah. So you align your sequences. Uh, you align the sequences throughout the whole bit of the sequences. But in the local alignment, you find the best areas of matches. Say, for example, in the certain portions where you have the best matches of your sequences. We'll look at that when we'll be looking at the dynamic programming algorithms and estimate the pros. So there are two differences. Global is along this entire sequence, and local is along the regions, the best matching regions. So we can show you, for example, so okay. Can you share? I wanted to show you the website. I don't know how. Can you share everything? Cannot share everything in the Zoom?
I think, Maksud, you need to share that window, the Chrome browser.
Okay. Okay, I'll just go through the slide then. Yeah. So this is Blast tool. This is one of the tools where you can align the two sequences. For example, you can provide one sequence here, and in the bottom, you have another option to provide another sequences, and you can choose the algorithm. So you choose a plus P, and there's some. So you can choose the algorithm parameters. So we'll understand. So we'll choose a matrix here, the Blossom 60. There are a lot of matrices here. We'll understand when you finish the lecture. And yeah, so if we just so you can see the descriptions here, and you can see in the last lecture we'll understand how the things look like. We'll be explained in details. So this is for example, this is the query sequence and the sequences in the databases. And if you see where you define the matches, identical sequences is provided in the middle. And to align it properly, there is a deletion of few bases here in the sequences available in the databases, and deletion of some bases in our sequences. So this is how they provide the gaps and tries to find the best alignment between the two sequences. The P databases, for example, the number of identical sequence of 149. So they are 79% identical. There are 40 gaps between them. So this is one of the examples been taken from, so this is a bit different. It looks a bit different than what we have shown so far. Yeah. So for example, here you have the identical sequences L, and here you got the plus sign because the leucine and valine, they're similar amino acids, not the identical. So you get the two score here, the identities. So that means 37 amino acids are identical to each other, and the 57 amino acids are similar to each other. So if you look at the identities, are 25% identical and the 39% similarity of the positives. And this will be explained in the last lecture, the E value or the expectation value. So the gaps, so you got the two gaps and the 1% of the gaps in between them two. So, and to find the score between these two sequences, yeah. So there are some matrices available. So that's arbitrary. That's basically depend on the algorithm you'll be using. So say for example, for if there is any matches, so you can provide a score of something like 1+1. If there is a mismatches, you can provide a score of 0, or and if there is a gap, so you can provide the -12 and a gap extension -1, something like that. So by providing the, here you can find the sum of matches 60, sum of mismatches -13, and gap, for gap you provide the penalty. So the total score is 35. So this the similarity score between these two is 35. We'll make it easier later once we finish the lecture. Okay, and we have shown that, so sometimes you need to put the gaps in between this while you do the PRS comparison, and you need to provide the values for that. For example, yeah, and AT. Yeah.
Recording in progress.
Okay, and say for example, let's just make it 10, so it will be easier. So for the match, I'll provide a score of +1, and for the mismatch, I'll provide a score of -1, and for the gap, I'll not show the gap extension penalty. That would be too difficult at this at the beginning. So for the gap, say for example, we provide the -2. Yeah. So how many we find the matches? Number of matches between them is 1, 2, 3, 4, 5. And the number of mismatches, so that's 5 times, let's provide 2. 5 times 2 is 10. And number of mismatches is -1 times. So we found the 1 here. So 1 mismatches, so -1. And then the gap, so the number of gap we found 1, 2, 3. So that's 3 times -2, -6. The total score between these two alignment is 10 minus 7 is 3. So this is how you determine this score. That's one of the ways. So that depends, obviously that depends on the algorithm you'll be using. So these numbers are not fixed actually. These are arbitrary number I've used. Okay. So one of the ways you can do the pairwise alignment is the dot plot. That's the simplest and the oldest method to compare the protein or the nucleotide sequences. So how can you do that? So write each letter of the sequence in the column and you put another in the rows, and you start filling boxes where there is a letter for sequence 1, where there's a common sequence between the 1 and 2, sequence 1 and sequence 2, and you can interpret the plot later on. For example, these are the two sequences, sequence 1 and sequence 2. Let's plot in the x-axis on the row and the column wise. Then let's fill that up. So we can fill that up something like that. Say for example, G, so there is a match here. So there is a match here There is a match here. There's a T match here. This T matching with this T. This T matching with this T. T, 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 and T. So that's T, 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 T. So here you got the C here. I'll not fill up the again, so I already filled that up. So this is how you do fill that up. Then what happens actually? You got something like that, and you look for the contiguous. So we can show that. So you look for the say for example, there's a you found one here, but there's nothing here. Yeah, so you don't use this one. So you can use the contiguous one. So this is one area. This is one area. So this is one area. This is one area. So these are the matching areas. For example, this is A, T, T, C. So that matches the A, T, T, C here. So this is T, T, C, T, A, T. And you got here, so T, T, C, T, A. So this is, and the parallel lines actually, so they are repeat regions. For example, this is parallel to this one. Yeah. And I can see that this is A, T, T. So, okay. So why is not matching here? They might, okay, that's good. Say for example here. Got here. So we got, so you look for the contiguous diagonals, like where you have the continuous boxes filled up. And you can see here that so A, T, T, C, T, A, and here. So it's a T, C, T, T, C, T. So basically, so the parallel lines shows us that there is a repeat regions here. So you can look for the repeat regions by sometimes what you need to do, for example, within your sequences. For example, if you have a sequences, year sequences, and you have to find the repeat regions within your sequences. So you can basically do the dot plot in gene or genome. Yeah. If you want to find the inverted regions, inverted repeats, it's not written here. So what you can do, you can dot plot against reverse complement of the same sequence. So what it means actually is, if, for example, you have the like, so what you need to do actually is you need to reverse complement this one, and if you plot them, you'll find the inverted repeats within these genomes. So this is very useful to find out the repeat regions within the genomes. So, for example, this is one of the alignments you get here. So, A, T, so that stretches over A, T, T. So here you gotta find match here. You can basically, so these are the matches here, dotted matches here. These are the mismatches here sometimes. And here, what you can see, you also find the insertion and the deletion. For example, there is stretches of matches here, and there is a certain break here, so there is no matches. So start, then you start matching, again. So that means there's a T that matches against this one, and it goes like that. But suddenly what you find here actually, so there is no matches here. So a gap here. Sorry, matches here, but a matches here, but there is a 2T here and only one single T here. So you put a gap here to get the best matches. Okay. So, but that was done like sometimes what happens if you use like, for example, only the using the only one word, yeah. So for example, A matches with the A, T matches with the T, it looks very fuzzy. For example, if you look for the nucleotide adenine, there's a 25% chances that you'll get that one. And and another example is like if you look for the A in the dictionary, so what you can find like many thousands of A's. But if you look for the A app, so the noise gets reduced. So you get the less number of words in the dictionary. So if you word the words, increase the word size, so you become more specific. In the same way, if you compare like A to A, yeah, or the T to, or the compare again only one word, so you get lots of noises. But if you increase the word size, for example, you're looking for the ATC or the ATG, something like that, or the TTC, so your noise level decreases. So for example, using the one word, so there is a transcript variant of A and C of one of the genes responsible for the in the Drosophila melanogaster. So they're using the one word size one, it becomes so noisy. And when they increase the size of the 10, so still you get some noises. But if you increase the word size of 250, the noise decreases significantly. So that's why you use it. We just don't do the dot codes with the arbitrarily. We use certain thresholds. So for example, so if you color in also with identical letters, some dots may be due to the chance similarities. As we said, that if you look for the one letter code, so the chance you'll have, there will be a chance that you're getting the similarities by chance. So use the window size. For example, you can use certain threshold. For example, the window size 3, and for example, you look for the word size 3, and the minimum of 2 matches. What it means, for example, so you're looking for the bean, yeah. So it should match at least two letters. For example, B or the IN or the BN. Yeah, at least 2 letters among the 3 word size. At least 2 should match. So that's how you build it up. So that's called the window size. Say for example, we look for the, and you should try to match it in the diagonally. It's not like that. This is a, say for example, it goes like that. This is a C, C, A, and we try to match the C, G, G, and so there is no match actually. So then we move to this diagonal. Yeah. So we are matching against C, T, A, C against T, C, G, G. So again, no matches. So you go like that. So you keep going like that. Then you move upwards, like you take from this one, and this one. So that's the G, G, C, and the A, C, C. So there is no match. But if you go like this one, for example, here, so you got the C, G, C, this one. Yeah, and matching it to G, G, C. So you found the 2 matches. Out of 3, we found the 2 matches. Yeah, so that's one of the, so we colored them, all of them, the blue color. Yeah, So that's one of the matches. For example, here you get the blue color. Then you move one stage, then you right. So let's now we keep going. For example, we are done with this one. Yeah. Now we look for this one, and this one. So that means G, C, T. So then G, G, C. It doesn't match actually, but G, C, T. So you go like that, and you can find that using the word size, you find a lot of noises here. So you can find a lot of places. But if you use the word size 3 actually, so you find these are the matching sites. These are the good alignment sites. For example, so yeah, so this gives you the good alignment set. For example, you can align that C, C, A, E. See this side, E, G, C, A, E, C, G. So these sides. This is a good alignment. So you can align them properly. So that's another another side that's the good matches is these areas. So this is how you find the best alignment site between the two sequences using the pairwise alignment technique. So that's the dot plot. And this is good for identification of long regions, strong similarity, and easy to make and interpret. Can be used for any length of sequences. Disadvantage: you need to play around to find the best window sizes. But if you, for example, if you use a very high window size, for example, you want to look for the 70 base pair long window size, sometimes you may not find any matches. Then sometimes you go 5 window size, you find a lot of matches, noises. So you need to do a lot of trial and error to find the best matches. And the graphical representation obviously doesn't give information about the mutations, so that which you can get in the easel alignment. What do you call if you align the. So then the different matrices came. So in the next class, we'll discuss about the matrices, but today we'll go to one of the algorithms. As we said, there are 2 types of alignment you can go through. We can do the, if your sequences are highly similar to each other, we will go for the global alignment. But if it's a diverse sequences, then we go for the local alignment. As I said, the global alignment is to align the sequences along the entire stretches of the sequences. But if it's a local alignment, you align only against the particular regions of the query sequences where you get the best matches. So one of the algorithms we're looking today actually, so that's a Needleman and Unz algorithm. So what do? We design a matrix along the x-axis and the y-axis, and if they're identical, a path along a diagonal can be drawn. So if they're identical, and it goes along diagonal, and we can add gaps along conservative substitutions. That's for the amino acid sequences, and we choose the scoring system. So there are 3 steps. We set up a matrix, score the matrix, and identify the optimal alignment. Okay. So if you find that our alignment is going along diagonally, yeah. So that means that's the match of the mismatches. And if it goes vertically, so there is a gap in the sequence 2 here. And if it goes vertically, so there is a gap in the sequence 1. So try to remember this one. So if it goes vertically, there'll be a gap in the sequence 2. And if it goes horizontally, so there is a gap in the sequence 1. And if it goes diagonally, there is a matches of the mismatches. Okay. Okay. Say for example, GLMT. So there is a matches. So it goes diagonally, GLBT, GLMT. So there are mismatches here, but even that it goes diagonally. But if GLT, if you put a like gap here or gap here, so gap in the sequence Actually, he was that is wrong. So if it's a gap here, so it goes vertically, and if it's a gap here, then it goes horizontally. Okay, let's see. Yeah. So if you like the two sequences F and D T P L and E, and there is another sequence one F K H M D E D P L E. Okay. So let's fill up the rows and columns. So it's F matches F. So we fill these boxes. M matches with the M here. Then E matches with the E here. So we fill that box up. So D, then the P and the P here. So it matches here, L here and the L here. We match up this A here and E here. So we match up again. So we fill up the shaded boxes. So how do we calculate that? So we try to find the maximum out of this three. So F, for example, so that's my, so that's a row one. That's if it's an I, this is a J. Yeah. So if it choose this on one of them, yeah. So here, so that's my I is equal to 2, J is equal to 2. If you look at it here, so I is equal to 3 and J is equal to 2. So now we need to find it. Yeah. So for example, if you have a yeah, and this is how we find the best score. So one value comes horizontally, one value comes from the vertically, and one value comes from the diagonally. Yeah. So the one that comes to the vertically, as we said, for example, A, T, C, G, and A, T, G. So we give a score for the match, +1 for the mismatch. So for example, for the mismatch, and we give a score of -2 here. So this is what we're using. And for the gap, we use a -2. Okay. So, and remember, so that Fij minus, so for this one, for example, if we take this one, so that's I is equal to 3, J is equal to 2. So your F I minus J will be J minus, so this value, the diagonal value will come from this one, the score of matching or mismatching here. So it will be clear to here actually. Say for example, this is my 1, 2, 2. So Fij means, so F that's 2, 2. Yeah. So my gap penalty, if you remember, that's a -2. And mismatch was -2, and match was +1. So if the value coming from, and we need to take 3 values. For example, for this cell, we want to take 3 values, one from this one, if I minus J, J minus 1 plus the score, either match or the mismatch. Okay, so it will come from diagonally. And another value that will come from here, if I minus 1 J, yeah. And another value plus gap penalty. So always if -2 if it comes from here, and if it comes value from this box, so that's -2. And if it comes from here, if for example, if it's a M, F, F, if it's a match, you add 1, or if it's a mismatch, you take the mismatch value -2 here. So here you go. So if you remember, yeah, so 0. So if it goes vertically, we always at gap penalty. So 0 minus 2 is minus 2. So minus 2 minus 2 is minus 4. You always the gap penalty. In the same way, you fill up the rows as well. So it's a minus 2, minus 4, minus 6, something like that. It goes like that. Okay. Okay. Now the value here is minus 2. So you always add gap penalty here. So gap penalty was minus 2. So minus 4 coming from here. So gap penalty minus 2, minus 4 coming from here. And here this is you have a F. So there is a match. So score for match is +1. So you had a 0 here. 0 add 1 is 1. So you're getting 1 from here, minus 4 is from here, minus is from here. Among these three, you take the best score. So best score among three is 1. Okay, do the same thing here again. So minus 4, minus 2, you get the minus 6 here. You get the 1 minus 2 is minus 1 here. At minus 2, so AM and F, this is a mismatch. So I'll minus 2, minus 4. So I'll take the minus 1, that's best score. So you go from here, then again minus 1. So you get minus 1 coming from here, minus 6 coming from here, and minus 2. This is a mismatch, so minus 2, minus 4 coming from here, so minus 1 here. So in the same way, you fill that up. So minus 1, there is a gap penalty always at minus 2 equal to minus 3. So this is a minus 1, minus 2, this is a minus 3 here, at plus 1, minus 2 because it's a mismatch. So this is the minus 1. So you get the minus 1, minus 3. So you take the minus 1 here. Now it trace back. Trace back means this minus 1 came from where? So it came from here. And this value came from here. This is from 0. So you trace that back. Yeah. So from where it came from, for example. Yeah. If you look into here, so this is a minus 4 coming from here, minus 4 coming from here. This is a match. So you get the 0 plus 1 is 1. Okay. So now you go there. Minus 1, minus 2 is minus 1. So minus 6. And here mismatch. So minus 4. So you take the minus 1 here. So here what do you do? Minus 3 coming from here, minus 3 coming from here. And this is a mismatch. Okay. So this is how we fill that up. And what you need to do, you need to arrow the path actually. For example, say for example, where this is coming. For example, this 1 came from here. Then this minus came from horizontally. This minus 3 came from here. So it's just denoted by the arrows from where it's coming from. Then you go to the right, the bottom right corner, then you find this one, this value. Now you trace back to where it came from. So this arrow came here from, this came from this minus, so we'll go backwards. This is called the back trace. Yeah. So, and this 5 came from this place. This 3 came from this 4. This 4 came from this 5. This came from this 3. This minus 4. 3, yeah, 3, and this one, yeah. So you basically find out the path from this value came from. Yeah. Now, if you remember what you said, if the value is coming diagonally, so there is a match or mismatch. If it's coming vertically, so there is a what you can say, there is a gap in the second sequence, and if it's vertically, so there's a gap in the first sequence. In this sequence. Here you go. So this is the path highlighted here. Yeah. Now we can determine the sequence very easily here. For example, So for example, let's say F, yeah. So F is coming diagonally. So that means there is a match here. So K, so that coming vertically. So there is a gap here. So H, that coming vertically. So there is a gap here. There is a M that came diagonally. So there is a match here. Now let's go to this three. So E, so there is a gap here. D, yeah, D came diagonally, so there is a match here. So now see, now there is a gap here. You put a gap here, and on the gap you find the T here. Yeah. So and after the T, the P came diagonally, so there is a match here. So then the 3 L came diagonally. So then you put a gap here. So in the gap you have the N here. The next one is E. So that came diagonally, so there is a match here. So this is how you align your sequences using the Needleman and Holmes algorithm. Yeah. Yeah. So yeah, in the next lecture, in the what you can say, in the next lecture, we'll show the Smith and Waterman. It's the same thing, but there is a only one difference is that you add 0 instead of the, you don't take the minus value and the negative value into consideration. So it's in the next lecture and the PAM matrices. I think I'll stop it here. Yeah. Yeah. So let's go through the question.
Yes, Maksud, please.
Yeah. So let's go. Please correct me if I'm Mohsin Mannan. Either they are not based on person similarity, meaning homologous in all or none phenomena. If it's coming from the ancestor, if they have the same ancestor, they're homologous. Yeah. And if they're not coming from the same ancestor, even they're similar, they're not homologous. Okay. Some books say it's 25%, some 30% in others. 25%. It's actually you need to work on a lot of experiences. So most of the books is 25%. So if it's below 25%, we call them the twilight zone. So it can be a match or it can be a mismatch. It depends on sometimes we work with the hypothetical proteins and we don't find the good matches. So sometimes we take the lower thresholds. Well, in most cases, I would say if you have like many alignments, just go more than 30%. Okay. Qualitative, but how much sequences are homologous to each other? The extent similar sensor. Okay, so we can't say that that's this much of homologous. We can say this percent of similarity. As we said, the homologous, they should came from the same ancestor, but usually they're similar to each other. But if it's more than 25%, we can say that they might be the homologous. Then the Sayyidan homologous chains will have some percentage similarity, while orthologous chains may not. No. Orthologous should have 25% similarities, but homologous may or may not have. Depends on the length as well. It's the twilight zone. Yeah, that's Wakase. Mohsin Manano. Yes, I recall now. Forget about the Jones. We used to use biotic software sequence alignment. We do have the option setting scoring metrics. On what ground do we discuss which scoring metrics to be? We'll discuss in the next class. So if it's like, say like, yeah, if your sequences are highly conserved sequences, then use a lower Blossom score. Sorry, higher Blossom score, and if they're diverse, you use the lower Blossom score. Are there softwares? We'll be using softwares. As we said, there are a lot of softwares, and I will be uploading this. What I'm going to do, let me share the assignments I have given you. I'll be giving it today. So you'll be using the software of your own. Let me show you. Okay. So here you go. Assignments. So I'll be giving the assignments where you will not be using the algorithm, but you'll be using the different softwares where you can use the different algorithms there. Yeah, there are a lot of softwares for the alignment, and you'll be doing it off your own. If it's struggle, then yeah, I'll upload the assignment just now after it's finishing the lecture. Any more questions? Oh yeah, Mosenman. Thank you, Mosenman. Yeah, thanks.
So thank you, Maksud. So we are on time. So if still there's any question or query or anything, just ask us at the Google Classroom. So thanks, Maksud. I think it is one of the most effective and brief way to cover this big topic in just 1 hour, and still you have next session as well. So it's really very exciting that you sum up this broad topic into one of the most definitive and usable approach. So so if still this query, you can ask us. We are here for a minute or so. Otherwise, we can leave. Yeah. And Maksud, you will upload the slides and
Yeah,
assignment
I'll upload the slides.
within a day or two. Okay. That
Yes,
would be
I'll
great.
upload the slides by tomorrow, but I will upload the assignments right now after the class.
That's great. That's great. Yeah.
Thanks, everyone.
So thanks, participants. Thank you, Maksud. So we will see
Yeah,
you next week.
See
Thank
you
you.
next week. Thanks, everybody. Bye.
See you. Bye bye. Take care. Bye bye. Akbar, you can stop the recording. Yeah.